Welcome to the third and final lecture video for our Class 21 series of lecture videos. In this video we're going to start looking at reactivity of alkenes, and we'll discuss reduction. So how does reduction go? Well, we talk about reduction as the addition of a couple of hydrogen atoms, and so we could definitely add hydrogen atoms to our alkene, make an alkane, so a saturated hydrocarbon. We use typically palladium or platinum in terms of a catalyst. Oftentimes it's a heterogeneous catalyst, so palladium or platinum, which is adsorbed onto carbon, which has a high surface area. Alternatively, we could use nickel or rhodium. There are other transition metal catalysts that are excellent catalysts for reduction. So typically we use 10% palladium or platinum on carbon. What is hydrogen bond worth? Well, our change in enthalpy for breaking that bond would be plus 104 kcals per mole. What other bond do we break? We break the double bond. The pi bond is worth 65 kcals per mole. But what do we form? We form two sp3 hybrid carbon hydrogen bonds, each of which are worth 100 kcals per mole. So it would be 65 plus 104 minus 200 kcals per mole, or about negative 31 kcals per mole. So we get heat out. It's an exothermic reaction. Many reactions are driven enthalpically, that is, they release heat. So delta G equals delta H minus T delta S. It's delta H that contributes to delta G being negative and the reaction being spontaneous. However, this reaction needs a catalyst, obviously, to proceed. So the reaction is exothermic, but it will not proceed without a catalyst. The catalyst we see most often is palladium on carbon, which is a heterogeneous catalyst, although we could potentially do these reactions with homogeneous catalysts, that is, catalysts that are dissolved in solution, so we have a single phase, as opposed to palladium on carbon, which is a solid catalyst that kind of floats in your reaction solution and stays solid. It does not dissolve. But of course you can filter that catalyst off after the reaction. How can we visualize the reaction? Well, here we've got palladium sitting on some sort of carbon surface. Hydrogen comes up to our palladium 0. That sigma bond sort of associates with a d orbital in our palladium, and it's split. And we call this palladium 2, we call this oxidative addition, because however many bonds to hydrogen or something else that our metal has, we call that its oxidation state, because hydrogen's more electronegative than palladium, so it really owns these electrons, and we must have taken 2 electrons from palladium in order to form these 2 bonds, essentially. So loss of electrons is oxidation. This is oxidative addition. Like I said, the sigma hydrogen-hydrogen bond can interact with an empty d orbital. Palladium has a +2 formal oxidation state in this representation. So the above process is oxidative addition. Then along comes our alkene. The pi bond can associate with the palladium, again with a d orbital of appropriate symmetry and phase. And as it does this, a hydrogen can insert onto one of those double bonded carbons, and we'll take the electrons to the other carbon and then use them to form a bond to the palladium. So we stay palladium 2 in terms of oxidation state. We've just changed one of the bonds from being to hydrogen as to now being to carbon. We call this insertion. Finally, there can be a reductive elimination, which regenerates our palladium 0 catalyst, and that would be where the hydrogen takes its 2 electrons, adds them to the carbon, and then The carbon gives its 2 electrons in this carbon-palladium bond back to palladium, and of course that's gain of electrons for palladium. It goes from a +2 oxidation state to a 0 oxidation state, and we get our hydrogenated alkane out the other end, which can no longer associate with the palladium. Hydrogenation is stereospecific, so those hydrogen atoms add to the same face. So our alkenes have 2 faces. We could have a top face and a bottom face. Those 2 hydrogens end up being added or bonded to the same face of the alkene. We call that syn addition. So here we've got a nice norbornene derivative with deuterium atoms, and this 1 carbon bridge is sort of shielding the top face, so our hydrogens actually have to come in from the bottom face of that alkene. That's why they add this way. And so we can tell how those hydrogens have been added with spectroscopic methods that we'll discuss later in the course. So that does it for this particular 3rd video in our Class 21 series of lecture videos. We'll start up basically where we left off in our Class 22 series of videos. Good luck with the question.